Hey everyone! Today, we're going to talk about something you see every day, even if you don't always realize it. We're diving into why the world isn't a neat, perfect bell curve. Instead, we'll look at a really powerful mathematical tool that helps us understand all the lopsided patterns out there. Everything from stock market returns to when our gadgets might fail.
Really, think about it for a second. We always hear about the bell curve, right? The normal distribution, where everything is perfectly balanced and symmetrical. But is that really how life works? Why are things like personal income or how long you have to wait for the bus almost never that neat? They're usually way more unbalanced and, honestly, pretty unpredictable.
So, on one side, you've got this beautiful, idealized world of the bell curve, super symmetrical. But then you look at the real world, and it's much more like what we see on the right. The data is skewed. Most of the values are all bunched up on the low end, and then you've got this long, stretched-out tail on the right. And that lopsided shape? Well, it tells a story that the perfect little bell curve just completely misses.
And that's really what we're digging into, this lopsided, skewed world we live in. These asymmetric patterns aren't just quirks. They are everywhere, defining everything from how much you might earn to when a server could crash. So to really get a grip on this, we need some special tools. Tools built specifically for this messy reality.
And these patterns are so common once you start looking. Think about something like executive salaries or real estate prices. Most of them fall within a pretty normal range, but then you have a handful of outliers that are just astronomically high. That's what creates that long right tail. It's the exact same deal with insurance claims. Tons of small fender-bender claims and then a few catastrophic ones. This is the world we're trying to model.
Okay, so the big question is, how on earth do we model a world that's so skewed? Well, this is where the hero of our story makes its grand entrance. It's time to introduce the gamma distribution. And trust me, this thing is a super flexible, super powerful master tool for wrangling this kind of data. So what is it? Put simply, the gamma distribution is a mathematical model that's custom-built for two things: outcomes that can't be negative, like you can't have negative waiting time, and outcomes that tend to be skewed. And the really cool part is that it's all controlled by just two little knobs, two parameters that let us mold its shape to fit all kinds of real-world situations.
Let's talk about that first knob. It's called the alpha parameter, but you can just think of it as the shape dial. By turning this one dial, you can completely change the fundamental shape of the curve. You can make it a really sharp, steep drop-off, or you can round it out into more of a gentle hill. It all depends on what kind of data you're looking at.
And then there's the second knob, the beta parameter. Let's call this one the scale dial. Now this one's different. It doesn't mess with the basic shape that you already set with alpha. Instead, its job is to either stretch the whole curve out or to squish it in, horizontally. So this is how you control the spread of the data, making it either really wide or super narrow.
All right, so because the gamma distribution is so versatile, you can think of it as having a few specialist offshoots that have their own very important jobs. They're part of the gamma family, and we're going to meet two of the most important ones right now. First up, we've got the exponential distribution. And here's the secret. It's really just a special case of the gamma distribution. It's what you get when you take that shape dial, alpha, and you lock it in place at exactly 1. Its whole specialty is modeling time. Specifically, the amount of time between random events, like how long until the next customer walks in, or the lifespan of an electronic component. Now this leads to a really fascinating and honestly kind of weird idea. What if a light bulb's past had absolutely zero effect on its future? What if it's already been running for 1,000 hours, and that tells you nothing, absolutely nothing about how much longer it's going to last? Kind of strange, right?
Well, that strange idea is at the very core of something called the memory-less property. And it's a unique feature of the exponential distribution. It literally means the system has no memory. The probability of something happening in the next hour is completely independent of how many hours have already gone by.
So here's a concrete example, a memoryless fuse. Let's say a fuse that has already worked for 100 hours is just as likely to last for another 50 hours as a brand new fuse, fresh out of the box, is to last for its first 50 hours. From a probability standpoint, the old fuse is just as new as the new one. It's a wild but really powerful concept when you're modeling things that fail completely at random.
Okay, so the other super important member of the gamma family is the chi-square distribution. If you've ever taken a stats class, you've definitely seen this one. It's another special case of gamma, and it is the absolute workhorse of hypothesis testing. It's the tool you use to figure out if your results are legit, like are the results of a political poll actually meaningful, or could they have just happened by pure chance? It's absolutely crucial for validating scientific research.
So this all sounds pretty abstract, right? Cool concepts, but how do we actually use them? Let's pivot and look at how engineers and actuaries put these distributions to work to make some really critical decisions.
Okay, check out this real-world problem. You've got a water pumping station, and in the afternoons, the demand for water can just randomly spike. A big enough spike could completely overwhelm the system. So the engineers have a goal. They need to set a capacity that's high enough to handle demand 99% of the time. How do they figure that out? Well, they model that afternoon demand using the exponential distribution, and that lets them calculate the exact answer they need.
And boom, there's the answer, 461 cubic feet per second. This isn't just a number they guessed. It's the perfect balance point. It provides that 99% reliability they were aiming for, but it also avoids overinvesting in a massive pumping station that would just sit idle most of the time. It's all about balancing risk and cost perfectly.
And you see the exact same logic in the world of insurance. Insurance claims are a textbook example of right-skewed data. So actuaries use the gamma model to figure out the pure premium, basically the expected cost for each policy. But maybe even more importantly, it lets them get a handle on that long tail, those rare but incredibly expensive claims. By modeling that tail, they can set smart policy limits and, this is crucial, make sure they have enough cash reserves to handle a catastrophe and stay in business.
All right, let's wrap this up. Why does any of this lopsidedness matter? After all this talk about skewed curves, what's the big takeaway?
Okay, here it is. First, the real world is messy and skewed, not neat and symmetrical. Second, the gamma distribution is our flexible, master tool for modeling all that skewness. Third, its special cases, the exponential and chi-square, are like specialists that handle specific jobs. And finally, and this is the most important part, understanding these patterns lets us all make much smarter decisions about risk, resources, and reliability.
So I'm going to leave you with a question to think about. Now that you can see these hidden patterns, where are you going to notice them next? Will it be in the financial markets? Or maybe in the lifespan of your phone? Or how about just your daily commute? I'll bet that now that you know what to look for, you're going to start seeing them absolutely everywhere.